Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com.
Hello, everyone.
Today we are taking a deep dive into two concepts from Unit 5, magnetism and matter, which are fundamentally important but often confuse students.
Magnetization, M, and magnetic intensity, H.
That's right. We are going to simplify these terms so you don't just memorize them, but truly understand the physics that, unlocks them.
Okay, I'm ready. These two always seem a bit tricky.
Okay, let's unpack this. Think about the most powerful magnetic action you have ever seen. Have you ever wondered how a huge electromagnet in a scrapyard crane can lift an entire massive car just by switching on a current?
Oh, yeah. The strength required must be enormous.
It is. And, it's not just big things. Here's where it gets really interesting for me. If I take a normal steel paperclip and just rub it against a permanent magnet.
The paperclip becomes a temporary magnet. I've seen that. It can pick up another small piece of iron. But how does that actually happen?
Exactly. How does the external magnet somehow transfer its magnetism to the paperclip?
That's what it feels like.
Well, that temporary gain of magnetism and the huge strength increase in the crane's electromagnet both depend on today's core concepts.
Yeah.
Magnetization, M, and magnetic intensity, H.
So it's all connected.
It shows that magnetism isn't just something that's permanently there. It's a response, a reaction from the material itself.
For a response. Okay.
So what does this all mean at the atomic level? The core idea is actually quite simple. Every piece of matter, whether it's highly magnetic iron or even non-magnetic wood, contains billions of tiny inherent magnets.
Tiny magnets inside everything.
Yes, we call them atomic dipoles. They arise from the spin and the orbital motion of electrons inside each atom.
Okay.
Now, magnetization, M, is simply a measure of how much those tiny internal magnets are aligned in one direction.
So like they're all getting organized.
Perfectly put. Think of it using our primary analogy. A crowd becoming synchronized.
A crowd.
Imagine a huge stadium crowd. Each person is one atomic dipole, and each is spinning a tiny magnetic wheel. Now, if everyone is spinning their wheel randomly...
Then there's no overall effect, just chaos.
Precisely. That's like an unmagnetized piece of iron. Now, if an external influence comes along, say, a huge magnetic field from a solenoid, that influence acts like a leader organizing them.
And everyone starts spinning their wheel in the same direction.
Exactly. That synchronized collective magnetic motion is the magnetization, M. It's the material's internal magnetic response.
Okay, so M is the collective effort of the material itself. But if we can already measure the total magnetic field, B, why do we even need this other concept, magnetic intensity, H? It feels like we're just making it more complicated.
That is an excellent question.
Yeah.
And it gets to the heart of why physicists invented H. They needed a way to mathematically separate two very different things.
Okay.
Imagine our solenoid again. The wire carrying the current, what we call the free currents, creates its own field. Let's call it B0. That is our input.
The field that would be there in a vacuum.
Correct. But when you put an iron core inside, the iron's alignment, M, creates an additional field. The total field B is the sum of both. So H is just a clever way to quantify only that initial drive, the field from the external currents alone, separate from the material's response.
So H is the cause and M is the effect.
You've got it. And for a mental image, just picture the material as a 3D lattice of atoms. Each atom has a little arrow, its dipole moment. Normally, they're all pointing randomly with total chaos.
Right.
When we apply an external field, those arrows start trying to rotate and align with it. The collective pointing direction of all those arrows and how strong that alignment is, that is magnetization.
Yes. The more arrows align, the bigger M gets.
Exactly. Now let us see how insert formalizes this idea. Could you please give us the exact textbook definition for M?
It says, we define magnetization M of a sample to be equal to its net magnetic moment per unit volume. M equals M net divided by V.
Perfect. That definition just translates our mental image into math. M net is the total alignment, the sum of all the tiny arrows, and dividing by volume just means M is the density of this alignment.
So it's like how densely packed the synchronized crowd is.
What a great way to put it. And M is a vector with units of amperes per meter. Now, let's bring in magnetic intensity, H. As we said, H represents the field from the external free currents alone.
Just the wires.
Yes. For a solenoid, the field in a vacuum, B0, is mu0 times N times I. We formally define H such that B0 equals mu0H. This means H is just N times I.
Ah, so H is just a different name for the field from the wires, but without the mu0 constant.
Essentially, yes. We do that because H is defined as the driving force, independent of the material it's in. H is the cause. Now, when we put the cause H and the effect M together, we get the total field, B.
Okay, so B should be the sum of the two parts.
Correct. The additional field from the material itself, Bm, is proportional to M. Specifically, Bm equals mu0 M, so the total field B is B0 plus Bm.
And if we substitute the definitions,
We get B equals mu0 H plus mu0 M. If we just take mu0 common, we arrive at the fundamental equation of this entire topic. B equals mu0 into H plus M.
B H plus M.
This equation is the heart of the chapter. It so elegantly connects the external drive H, the internal response M, and the total measurable result, B. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.com.
So we have the main equation. Now, how are H and M themselves related?
Good question. For many materials, especially those that aren't strongly magnetic, the response M is directly proportional to the applied intensity H.
So if you double H, double M.
Exactly. And we introduce a proportionality constant called magnetic susceptibility, chi, to describe this.
Spelled C-H-I?
Yes, the Greek letter chi.
Oh.
So the relationship is simply M equals chi times H. If a material has a large chi, it means it magnetizes very easily, even with a small h.
Okay, and chi is just a number, no units.
Correct, it's dimensionless. Now let's do a simple example to see why this matters so much. Remember the scrapyard crane? Imagine the iron core inside its solenoid. Let's say the current in the wires creates a magnetic intensity H of 1,000 amperes per meter.
Okay, so that's the input drive from the crane.
Correct. Now we put iron inside. Iron is strongly magnetic. It has a high susceptibility. Let's say chi is around 200.
Wow, that's a big number.
It is. So what is the material's response, M? Well, M is chi times H. So M is 200 times 1,000.
That's 200,000 amperes per meter. Wait a minute. So the material's own internal alignment is 200 times stronger than the field we created with the wires.
Exactly. The material is doing 200 times the work. Now let's find the total field B.
Using B equals mu0 H plus M.
So we get B equals mu0 into 1,000 plus 200,000. That's mu0 times 201,000. The total field B is about 201 times stronger than the field you would have had in a vacuum.
That's incredible. That 201 times amplification explains the crane perfectly. The current provides a little push, H, which triggers the ion to give this massive response. M, this is actually so useful.
It truly is. And this susceptibility, G, is what defines the magnetic personality of a material, depending on whether G is small and positive, negative, or very large. We classify all matter into paramagnetic, diamagnetic, or ferromagnetic materials. Understanding H and M is the absolute key to that entire topic.
Got it. It all builds from here.
Okay, now let's talk about the silent killers, the 3 misconceptions that frequently lose marks for students in exams.
Oh, this is important.
Misconception 1. M and B are the same thing. Students often use magnetization, M, and the total magnetic field, B, interchangeably.
I can see why. They both describe something magnetic and their formulas are linked, so why aren't they the same?
Because they represent completely different physical ideas.
Yeah.
M is the material response. It tells you only about the alignment inside the atoms. B is the total field. It's the physical force you can actually measure. M is just one component that makes up B.
So M is the internal story. B is the final result.
Perfect. Remember that.
Yeah.
M is the material response. B is the total field. Now, misconception 2. Magnetization is unlimited. Students assume that if you just keep increasing the external field H, the magnetization M will also keep increasing forever.
But wait, if M depends on aligning the little atomic arrows, there's only a limited number of them, isn't it? They can't align more than 100%.
Exactly. You've hit on the key point. M saturates. It reaches a maximum value. Once all the atomic dipoles are perfectly aligned, M cannot increase any further, no matter how strong you make H.
So M has a ceiling, a limit.
Correct. And finally, misconception 3. H is the field inside the material, and B is the field outside. It's a classic confusion about location.
Right, like H is for inside and B for outside.
That's what many think, but it's wrong. Both H and B exist everywhere inside and outside. The distinction is based on the source, not the location. H is caused only by the free currents in the wires. B is caused by both the free currents, AD, the material's magnetization.
Ah, so it's about what's creating them, not where they are.
Precisely. It's a source-based distinction.
That clarifies things so much. M has a limit, B is the total sum, and the HB difference is all about the source.
To lock this down for your exams, let's go over a few memory anchors.
Okay.
First, the mnemonic or chant for the main equation. Let's just repeat this in our minds. B equals mu0, H plus M in parentheses.
B equals mu 0, H plus M in parentheses. Simple enough.
Now, for the catchy phrase that defines their roles. H drives, M responds, B is the total.
H drives, M responds, B is the total. I like that. It summarizes everything.
And finally, a physical gesture. Try this with me. Point your right hand straight forward.
Okay.
That's H, the driving field from the current. Now, slightly curl or clench your fingers.
Right.
That's M, the material's response. The total effect, B, is the overall strength of your hand, the combination, the total force you feel.
Drive, response, total. That actually helps visualize it.
Great. So let's quickly summarize the 3 most exam-safe factual points you should remember.
The key takeaways.
First, magnetization M is the magnetic dipole moment per unit volume. It represents the material's inner magnetic alignment.
Okay. M is internal alignment.
Second, magnetic intensity. H is the magnetic field created by external free currents alone. It is the driving force.
H is the external drive.
And third, the total magnetic field, B, is the superposition of these two, given by our key equation. B equals mu 0 into H plus M.
B is the total result.
Got it. Understanding these 3 points is crucial to ensure you understand all your concepts this deeply so that getting maximum marks in 12th CBSE physics, chemistry, and maths becomes a natural outcome. Do visit ProfSam.com.
That is ProfSam, right?
Yes. Thank you for diving deep with us today.
Thank you. This was really helpful.
All the best for your studies.